So I have, in fact, one very good problem from your own book that I found. I'm going to do that one. And let's see if I can locate it. I misplaced it. Okay. All right. So, I think I started a problem that we did not finish last time, right? Am I right? Do you want me to complete that one or do this one? Because this one, I like it because it's a little bit more complicated. That one was easier. So as long as I find that function, okay? Like, let's see. I'm not sure where it is. Okay, so never mind. I'll just do this problem. So let's just consider something like this. I believe it was this problem. So this was A, this is B, this is Y2, Y1, which was K1 X squared. This one was K2 X half, something like that, okay? So we want to find this moment of inertia of this shape about X and Y axes. First, let's find those constants given the coordinates of this point that is given, right, at A and B. So if I substitute that here, we have B is K2, A 1/2, so that will give me K2 is B over the square root of A. So Y2 is simply B over square root of A X to 1/2. Here, you have B is equal to K1 A squared, so K1 would be B over A squared, therefore Y1 is B over A squared X squared. So these are the two functions, and we want to find a moment of inertia of this area surrounded by these two curves about the X and Y. Remember that Ix is the integral of y squared dA, and Iy is the integral x squared dA. So the only thing you really need to do in this case is to set up the right dA differential area in each case. And as I said, for I of x, you consider a differential area whose sides are parallel to the x-axis. In other words, this is dy, therefore this would be the x that you find from this function, I call that x1, and this is the x from that function, x2. So for this case, dA is what? Is x1 minus x2 times dy. So it will be a function of y. For this case, for the case of I sub y, you need to consider a differential area whose sides are parallel to the y-axis, or this is the x, therefore this is y from this function, I call that y1, and this is y from this function, y2. So dA in this case would be y2 minus y1 times dx. Okay. So That's the step one for finding the moment of inertia of general shapes. So let's just start with I of x. Yes?
Why are you substituting out x, putting in a, making that equation equal to b in order to
This one you mean?
above, when you're taking y2 equals k2 x to the 1/2, and then you're substituting a for x.
Oh, you know, the k is k1 and k2 are some parameters,
Right.
unknown parameters, right? You need to find them in terms of the given values here,
Oh, so we're talking
which are
about
a and b,
okay.
right? So
Got
let's say a and b are given 1 and 5 or something like that. So you can find the values for those parameters. That's why. So I'm substituting to find the actual value of the function. Any other question? So let's start with Ix then, right? So we first set up dA. You need to find x from this function. This is the function. So if you want to find x from this function, x1, right, which is what you need from here, would be what? Would be y a squared divided by b, the square root of that. So it comes out to be this. That's x1. x2 is from this function. So you need to square the two sides and in order to find x in terms of y. So you'll have a y squared divided by b squared. So that would be the a. So just simply substitute that in here. So I of x then would be the integral of y squared times this. And I'll take a out, because it's a common between the two. So you have the square root of y divided by the square root of b. Okay. Minus y squared divided by b squared dy. And y changes, in this case, goes from 0 to b to cover the entire area, sweep the area. So this goes from 0 to b. So let's perform that integration. We get integral from 0 to b, of multiplying that, we get 5/2 over square root of b, right, minus y4 over b squared dy. And if you simplify that and perform the integration, you get 2/7, okay, of square root of b, y 7/2 minus 1/5 of y to the 5 divided by b squared from 0 to b. Okay, substitute for b, you get 35 divided by 7. Okay, you get 3a b cubed over 35. So that's going to be I of x. Okay, but forget about mathematical derivations. The key is to set up dA. Once you set up dA, you just have one integral to evaluate, and that's it. Okay? You do the same thing for I sub y. That is, you need to put I sub y, okay? You need to set up dA, which in this case now would be a function of x. And dA is this, which is, we set it up. y2 is this, so you have b over square root of a, square root of x, minus y1 is b over a squared x squared dx. So I of y is the integral of, and now in this case I take b out, x, square root of x divided by square root of a minus x squared divided by a squared times x squared dx. So let's simplify that, you get b, and dx changes, in this case, goes from 0 all the way to a, so that's a bound of integration. So you have this times what? You have integral from 0 to a of x 5 half over square root a minus x 4 over a squared dx. Simplify that, you get, and perform the integration, you get, again, 2, 7, okay, x 7 half divided by square root of a, 7 square root of a, minus 1/5 x to the 5 divided by a squared, 0 to a. If you perform that and simplify this, you get I sub y comes out to be 3b a cubed over 35. Okay. So for the case of general shapes given by, due to intersection of two curves or three curves, doesn't matter. It may have more than two functions. Doesn't matter. All you need to do, set up the DAs, see how you can basically relate that to give the functions given. Once you set up the DA, set up this corresponding integral, bounds of integral are clear, it's based on variation of dy or dx, perform the integration. Yes?
Can you show again the replacing, I mean, like k equals b over root a? How did you?
Oh, here?
Yeah.
Yeah, this is, if you don't mind, I will just erase this part here, okay? So let's say you had this function, right? Or these two functions. Let me just start with this one. You have y is equal to, let's say, k x over half. This is unknown, right? But you do have the coordinates of one point on this curve with y of b and x of a. Let's say this is 3, this is 5. So you can find the unknown parameter, so write the specific form of that function. So at this point A, right, y is 5, x is 3, right? So that will give you
Okay.
k, but in this case was in terms of b and a, so that would be just that, right? Any other questions? So as you can see, this case of area given by some mathematical functions is not fun, right? It's something that is good for a calculus course. It's really not something that you come across much in a real practical application, except somebody wants you to find a moment of inertia for a crazy shape or some architectural drawing or something like that, right? In general, most common cases that you come across are, for the second case, composite shapes, okay? So let's talk about composite areas now. Composite area. similar to what we discussed in centroid. For all simple geometric shapes, a rectangle, a triangle, a circle, half a circle, quarter circle, there is a table in the back of your book that tabulates the moment of inertia of these shapes about their own centroidal axes. You remember the centroidal axes? Centroidal axes are axes that go through the centroid of the shape. So you need to find the centroid of the shape, draw those, right? So moment of inertia for those simple cases are tabulated actually both with respect to the centroidal axis of those shapes and also some axes that are parallel to those. So for the composite areas, what you really need to know is, number one, that table for I of simple shapes. For instance, if you go there, you see that if for a rectangle of width b and height h, I with respect to the centroidal x-axis and y-axis are tabulated. You see that I of x is 1/12 of b h cubed. How did they find these? The same way we did it. Let's first show how you can derive this if you want. Okay, how do we do that? Say I with respect to this axis is the integral of y squared dA. And what was dA? Is a differential area with sides parallel to x-axis, right? So I will do that. So this is dy, and I'm going to find that, basically with respect to this axis, except that in this case, the width of this area is constant. So dA in this case would be just simply b times dy. So if you want to perform this integration, right, this y varies from here to here. But since this area is symmetric with respect to this axis, I consider half of this area, multiply that by 2. So this would be simply 2 times the integral going from 0 to, this is h over 2, okay, y squared times dA, which is b times dy, or would be simply what? Comes out to be 2b, b comes out, right, integral from 0 to h y squared, okay? And if you substitute that, you get 2b, right, times 1/3 of y cubed going from 0 to h cubed. So if you substitute for y, simplify it, you will get 1/12 bh cubed. That's how that value is found and tabulated in the book. And they've done it for all those shapes, okay? So that's the first thing you need to know. The second thing, which is important, is parallel axes theorem. How many of you remember that from calculus? What was it?
Physics 1, wasn't it?
Physics 1, doesn't matter, somewhere.
Oh, God. Isn't it like oh, no.
I'll make it a
It's
lot
been a
easier.
while. I remember
If you
it.
have an area,
Yeah.
it came down to this, and you have the moment of inertia of this area with respect to any given axis. In other words, if you can find the moment of inertia of that area with respect to this axis, and now if you're asked to find the moment of inertia of that area about an axis that is parallel to it, okay, where the vertical distance between these two, say, is d, you don't have to go through the pain of redoing the whole thing.
Mm-hmm.
moment of inertia of that same area with respect to this new axis is what you had already calculated plus the area times the square of the distance between the two. This is a very powerful tool that comes quite handy. Even here, if you look at those tables in the book, moment of inertia is given with respect to this, and for instance, this axis. And you wonder how they've done it. They haven't recalculated it. You have the moment of inertia with respect to x bar. If you want to find moment of inertia about x, you just simply write 112 bh cubed plus the area, which is b times h, times the square of the distance between the two, which is h over 2 the square. So if you simplify this, you see that this comes out to be bh cubed over 3. Okay? So that's how those are tabulated. But these are two important pieces, or in fact, all that you need to find the moment of inertia of a complex composite shape, okay? So with that said, let me show you through an example how you do it. Very easy. Oh, number 3, before I forget. Although it's obvious, okay? But I'll show it to you as a third concept, if you will, that to find a moment of inertia, okay, of a composite shape is equal to the sum of the moment of inertia of each sub-area. In other words, you want to find the moment of inertia of the big area, you can just divide it to sub-areas, find the moment of inertia of each sub-area with respect to the axis you've been asked to find it, and add them up. Consider, again, those areas that do not exist punched out as negative, exactly the way you treated the centroid problem, okay? So, with that said, let me just demonstrate the concept through an example, unless you have a question. No? Okay, so I have prepared a good problem here. The problems for the composite shapes in your book are just too simple. They consist of mainly 2 areas. So I don't know why. All the problems, I looked at almost every single one of them. So, of course, makes it easier to do, but it doesn't give you enough practice. So I hope you find mine more challenging. So let's see. So this is the problem that I had made up. This is 20 and this is 20, okay. Okay, so this is 20 meters. This is 20 meters. So this is 10. I will cut, this is, let's say this is 10. Okay, let's see, we cut a quarter of this piece. So this is 5 meters, this is 5 meters, okay? Then here, I will cut a half a circle, a shape, like a half a circle also, okay? So this is the area of this is a 2 meter radius. And then come here, and I will do this. So this is 5 meters. So I want to find this, the moment of inertia of this shape about, let's see. In fact, let me pause here. Usually in moment of inertia problems, there are two types. In type 1, like, okay, type 1, of course these types, I've made it up myself, so. Type 1, you're given a shape and you're asked to find the moment of inertia about a given set of axes. In type 2, okay, you're asked to find moment of inertia about centroidal axes. Do you remember what centroidal axes were? You find the centroid of a shape, the axes that pass through that are called centroidal axes, right? I prefer the second type, because that's what you actually will need in the next course. We assume, you will see, I'm not going to confuse you, that centroidal axis and neutral axis coincide. If you have a homogeneous, blah, blah, cross section. Centroidal axes have a significance when it comes to your next course. Those are axes about which, as, say, for instance, a cross section is subjected to deformation or bending deformation, layers along those axes do not actually go through deformation. I don't want to confuse you, you don't even understand what I'm talking about, but given the fact that this whole concept, as I've said, belongs to the next course, but we cover it here. But I just want to tell you, at least alert you, that this is more important. And that's, in fact, why I emphasize it. So, long story short, I'm giving you this shape. I want you to find the moment of inertia of this shape about its centroidal axis. What does that mean? That first you need to find the centroid of this, draw those axes, then find the moment of inertia about those axes. The tools you have is that table and parallel axis theorem, okay? And the step 1 is always, you must know it by now, is what? Step 1. No, we have already given you this coordinates we're talking.
Oh, split it up into different
Split it up.
Free body diagram.
Yes. Does he deserve some point? Right?
No.
You didn't get a vote of confidence, so, okay. So let's divide it to sub-areas. Okay. He's a friend. Okay, true friend, okay? So he was honest. But anyway, so let's divide it up. This is how I'm going to actually divide this up. To make it easy. You can do it in so many ways, right? The general advice is try to use as few number of areas as possible, right? Because you can consider this an area, this an area, this an area, this is an area, that's one. Or maybe this is one area, you've cut this one out, this is an area, you've cut this one and that one out, and this one out, so you end up in that case 6 or 7. But the way I'll do it, I would end up with only 4, okay? And this is how I do that. I consider this as A1, which is obviously negative. I consider this as A2, also negative, and this is area 3 that is cut out, so that is negative, okay? So this would be area 4, okay? So that's the step 1. What is the step 2? Table, yes. To save time, I've already set up the table there to save some time. So that is step 2, okay? Okay, so this is how that table goes. You're familiar with a good part of this. You want to find the moment of inertia by the centroid of the shape. So you need to find its centroid. So, right, these areas, right? A1, A2, and A3, and A4. These are all negative, so label them accordingly. You need to find those areas in meters squared, the units, right? So area 1, pi times r squared, which is 4 divided by 2, so it would be 2 pi, right? Right? This is area 1. 2, so pi r squared, pi 4 divided by 2. Area 2 is that triangle. 10 times 5, 50 divided by 2, 25, negative. Area 3 is that square. Here, 5 times 5 also happen to be 25. And area 4 is a large square that you have, so that would be 400. Second column, okay, you know by heart now, right? So you set up xi, which is the distance from y-axis to the centroid of each of these shapes. So for A1, you know that, this is what? 4 times r divided by 3 pi. So this is x1 bar. For this guy is this 1/3 here, 1/3 here. The 1/3 here, this is 10, right? So this is 3.33, 1/3 here, 1/3 of 5 is 1.67, right? So this is x2 bar. For this guy is right here, so that is what? That is 2.5 plus that, 17.5 meters. So just tabulate them. And for this guy, obviously in the middle of it, so it is 10. So this is x4. So let's just write them down. So for x1, I have calculated that. I'm just going to quickly write it down. Okay, that would be 18.85. For the other guy is 3.33. Then I had 17.5, and then 10. So the next column was what? Yes.
8 divided by 3 pi.
Is it 2 pi?
Which one?
The 4 times 2 over 3 pi.
No, which area? are you
A1.
looking at? This one, 8, 3.
Oh, plus, never mind.
Right.
It's
Plus
So, yeah,
18 or
that
whatever.
should be
17 and a half.
right. So
18.
For this, then the next column was what? XI, right? So would be this times that for all of them. I'm going to write them down again. So 118.4, and that is negative. 33 times 2.5 would be 83.25 negative. 17.5 times 25 would be 437.5 negative. This times that, 4,000. So this will give you what? Summation of AI, XI. This will give you summation of AI. I have the numbers here, 343.7. This one is 3361, 3,361. So if you divide this by that, it will give you X bar for this shape, comes out to be 9.8 meters. So the centroid of that shape is along this line, which is going to be y axis of the centroid, or centroidal y-axis, and this distance is 9.8. So where is it located along this line? You need to find y bar, right? You remember that? So you find y, I, okay? So for this guy is this, right? This is y1, which is 10. For this guy is this, y2, which is 10 plus 1.67, so it would be that. For this guy is y3, which is 17.5, and for this guy is y4, which is 10, right? So again, just tabulate them. So you have 10, you have 11.67, you have 17.5, and 10. And then YIAI. So multiply these again, and I'll give you the answer. Just multiply YI column by AI column, so you get 63 negative. You get 291.75, 437. No, that would be, yeah, 437.5, yes. Should be the same, okay? And then 4,000. So if you add these up, you get AIYI, right? And I have the answer here. You get 3707.08. No, 32, okay, 08 point, no, 07.8. So if you divide this by this value, you get y bar. That comes out to be 9.3 meters. So that means the centroid is located at, this is 10, so it would be, this was, maybe I will label that with red. This was 9.8 for X bar. For Y bar is this. This is Y bar, which is 9.3. So this is the centroid. And this will be the centroidal X axis. Okay? That's now what the problem is asking you. To find the moment of inertia of this whole shape about these axes. So what do you do now? You find this. You form a new column. Call that I sub each area about its own centroidal axis. I call it like this, for the lack of a better notation. So what you do, you find the moment of each of these areas. For instance, this guy. You have this, you have this, you have this, right? All of these. Each of them has their own centroidal axes, right? This is the X centroidal axis of this guy, X of this guy. These are the values that are tabulated in that table. So for instance, for a half a circle, which is area 1, you go here, you see it's given as 1/8 of pi r to the 4. So I will write it down. 1/8 pi r to the 4, that is given, that will be 6.3. Remember, this is negative. So we are going to find now, what we are trying to do is to find a moment of inertia of this whole shape about this axis. So I'm finding first moment of inertia of each shape about its own x-axis, and then I form another column, which is a moment of inertia of that same shape about this new axis. I don't have to do much of calculation anymore, because that would be what I found here, okay, plus the area of each shape times the distance squared between those two axes, okay? So, for instance, this area 1, this is the centroid of that area 1, centroid of the axis of x, 1 bar. This is the axis about which I want to find it, right? I have this one, which is that column, the value I've just found. All I need is to find this, which is D1, right? And I have that. This is 10, this is 9.3. So this is 0.7. So what I would do here, I write 6.3 plus the area, which is pi r squared over 2, right, times 0.7 squared. And that's the moment of inertia of that shape about that axis. And that comes out to be, okay, 9.4 negative. Same thing with 2. I will find a moment of inertia of this shape about this axis. You go to that table, you will see that for a triangle of base B and height h, moment of inertia, okay, about this centroidal axis is 136 BH cubed.
Is that a pi?
Yes, this is a pi, right. It's not a nice looking pi, so let me make it more. Okay. So let's evaluate that. If I calculate 136, this is B, this is H, 10, 5. So I have 1 over 36, 10, 5 cubed, okay? And that's gonna come out to be 34.7. So this would be 34.7 plus the area of that triangle, which is, you already have that, 25 times the distance squared from here to here. This is 9.3, right? This was 11.67. So this distance, which I call that D2, would be 11.67 minus 9.3. So it would be 2.37. Okay, so 2.37 squared, okay, for that, or 2.4 squared, that will give you 174.3. You do the same for this guy. This is a rectangle, right? So if this is B, this is H. Moment of inertia of this guy about this axis is 112 BH cubed. So it would be 112, 5, 5 cubed. You simplify that, you get 52.1 meter to the 4. So moment of inertia of this guy about this axis is its area times this D3 squared. What is that D3? This is 9.3, right? This was 17.5. So that would be 17.5 minus 9.3, so it would be 8.2, right? So you just simply write down 52.1, okay, plus the area that you have, 25 times 8.2 squared. So that will give you, okay, 52.1, and that was 1,733.1, and that is negative. This other guy, the last one, this big guy, this is 9.3. The centroid of that shape is at 10, so the distance would be only 0.7. So, first of all, its own moment of inertia is 1/12. B, which is 20, times h cubed, which is also 20 cubed. So that would be 13,333. Okay, so this is 13,333 plus from the area, which is given 400 times 0.7 squared, and that comes out to be 13,347.3. Okay, a lot of work. Well, you have to hire an accountant to do all, to keep track of all these for you, right? So now you're done. We said moment of inertia of an area with respect to any axis is the sum of the moment of inertia of each subdivision, right? So you just add these up, and you have I of that shape about the centroid of this shape, and I'll give you the answer. That comes out to be 11,612.5 meter to the 4. Are you done? No! This is just the beginning. Now you need to do the moment of inertia by the y-axis. So just repeat this. You find the moment of inertia of each shape, right, about the corresponding centroidal axis, y-axis of that shape now, about these axes. Okay? They're tabulated. You find them. Then you add again the moment area times, I call d prime I squared. Now, this is the y, so it would be this distance, right? In other words, for this guy, it would be the distance from here to here. For this guy, distance from here to here. For this guy, it would be this distance, and for this guy is this distance. Okay? Calculate all those.